I'd like to thank everybody for joining us for today's WebEx conference. We'll take about another few minutes to allow additional participants to log in. Rick, you should have controls of the WebEx at this point in time.
Okay, Christopher. I see the indicator at the bottom left of my screen, so we're good to go.
Okay. All right, if we're ready to go. My name is Jeff Donato. I wanted to introduce Christopher first. He's going to go through and tell you who you all are, but I wanted to thank you for attending the first virtual stationary battery and DC power conference. This is really intended just to be a fun event that we can get together and discuss questions and issues that you may be having in the DC power segment of our industry. And this is something designed to be free of charge and at this point, and be very open to questions. So the format, we have all your questions from the registration process. We do thank you for that. So we have over 100, and Rick Tressler will be running through those questions, and the panel will answer those. But first, I want to introduce Christopher. Christopher is a volunteer leader with the IEEE. And if you don't know, the IEEE is a professional organization with over 425,000 members. And they develop the standards and basically rules that governments, companies, and organizations like the National Electric Code and recommend and follow. And there's a lot of other committees that go over things like artificial intelligence, big data, and most importantly, ethics as well. Chris is in the Region 5 South Area Chair, serving over 25,000 members. And he is also the recipient of the Region 5 Jim Leonard Outstanding Member Award, which is a very prestigious award in that section. But today he's going to be moderating technically for us and making sure that we are running smoothly. And he's also going to be transferring passing the ball basically to the panelists to be able to show any kind of evidence or proof of the things that they talk about. So you have to bear with us when we first start. It'll probably go smoothly, but we ran a dry run yesterday, so everything should be okay. But I will pass this over to Christopher, and you can introduce the panelists.
Thanks, Jeff, for that wonderful introduction there. Rick Tressler, who's actually going to be the main moderator of this particular conference. And so Rick is going to be managing all the different questions, as well as the different guest speakers that we have today. We have Mr. Kurt Ashton joining us as well. And Mr. Kurt, I may mispronounce your name, Kurt. Your last name is Euler?
Very good, Christopher.
All right. And then we also have...
Good morning.
Good morning, sir. We also have Miss Leslie Varga. So with that being said, let's do just a quick introduction of each one of the different participants. You probably know more about your background than I necessarily know, and I don't want to miss anything. So with that being said, I'd like to at least turn over to Rick first to go ahead and share a little bit about his background.
Okay, very good. Well, good morning, everyone. And thank you very much for taking the time out of your schedule to join us for a couple of hours here today on WebEx to talk about energy storage and DC power systems. I'll just be really brief. I've been working with standby batteries for over 35 years. I've got 10 years prior experience as an industrial maintenance and construction electrician. And I've spent the majority of my time with Emerson and Albert, which a number of years ago became one and the same. And I provide technical support, training and education services under my company's badge, Rick Tressler LLC. So things changed back in mid-May, and the short story is here we all are doing what we like to do, but doing it virtually. So it's a pleasure to be on here, and I'd like to thank Jeff for his involvement in this. We started talking about 7-8 months ago about doing training and education services, and it's one of the reasons, it's the main reason that I'm doing this today. So back to you, Christopher.
Thank you, Rick. I really appreciate that. With that being said, I'd like to pass it over to Ms. Varga, Ms. Leslie Varga. Could you please tell us a little bit about yourself?
Sure. Thanks, Christopher. Yes, I'm Leslie Varga, and I've been in the stationary standby power industry for over 30 years. I'm an electrical engineer, a PE, and I've been a member of the IEEE Stationary Battery Committee for 25 years plus. I'm recently a former business owner where we did engineering, furnish and install services for end users of standby power systems. And my area is predominantly lead acid and nickel cadmium.
Thank you, Ms. Leslie. Really appreciate that introduction. Jeff, do I need to turn Tom back over to you and allow you to introduce yourself as well?
Sure. My name is Jeff Donato. I've been in the industrial battery industry for this is my 25th year. I started out in motive power for a few years and then switched to stationary power systems right around 1998. And I've worked for a few reps of battery companies in that time. And then I went to go work for Emerson Network Power for about 9 years. And today I am the CMO for EnviroGuard, and I've been there for about 5 years. And so I have a well-rounded background with applications of battery systems in telecom, utility, and data center. But have spent my time in the regulatory area with EnviroGuard over the past 5 years. I'm a member of the IEEE ESSB group and chair of the 1578, which is spill control and neutralization standard. Thank you, Christopher.
Thank you, Jeff. Really appreciate that. Again, I just wanted to remind all of our participants to please feel free to type your questions into the Q&A box. And we'll be answering those throughout the presentation here. Curtis, could you please introduce yourself, sir?
You bet. Like the rest of them, I've got 30 plus years of experience in the standby battery world. I'm an electrical engineer and an electrician. But I started out right out of high school, and I remember second year on the job working as an electrician's helper in a coal-fired power plant, walking into the battery room, taking specific gravity readings and voltages. And I asked the electrician what all those numbers meant, and he said, I don't know, I just give them to the boss. So our goal here today is to help you know a little bit more about what those numbers mean. I worked for 25 plus years for telecommunications and data center company. And now I work for a battery manufacturer under a division that does DC services. So like Leslie talked about with her company, install, engineering, maintenance, all that type of stuff. And so I have a lot of experience with all kinds of different batteries, a lot of lead NiCad, nickel metal hydride, lithium ion, whatever. So I'll save the rest of it for later.
Appreciate that, Curtis. Thank you very much. And Kurt, could you please introduce yourself?
Well, thank you, Christopher. Good morning, everybody. I'm Kurt Euler, and I'm starting my 40th year in the industry. I started with electric utility in Northern Illinois, and I worked in the nuclear generating division, and I was the stationary battery and DC auxiliary power system technical expert. And then for both the nuclear division and then later on for the transmission and distribution side. So most of my background is electric utility. I was former owner, founder, and president of Standby Power System Consultants until 3 years ago, and passed the ownership on to H.M. Craig Company out of Edina, Minnesota. So it's good to be here. It's good to be all these folks on the panel are dear friends, first and foremost, and colleagues who we all go work on the IEEE, various different IEEE committees. So with that, back to you, Christopher.
Well, thanks, Kurt. My fast math is about 160 years of battery expertise on today's call. And that's truly, truly amazing. So I am honored to be here. I'm honored to learn more about the business. And this is one of the few places in the world, as far as I'm concerned, from an IEEE perspective, is that this is the UN of the electrical industry. So we don't necessarily have competitive my battery versus your battery, or I know more than you do. This is all a collective of sharing knowledge, and that's the full intent. So with that being said, I'm going to turn over to Mr. Trester and go to mute and start answering some of these questions here.
Okay, very good, Christopher. Thank you very much. And it's very, very good to be with everybody here this morning here on the panel, and with everybody that has registered and has logged in today. We're going to get right to this. We've got about an hour and 50 minutes available here to go through questions. And I'm going to start with the first one, and it's in a category of battery monitoring. And the question is, and it is a two-parter, so we'll get the first one out of the way, and then we'll go to the second part after we answer the first. Battery monitoring systems have been used successfully for many years, but quarterly battery maintenance is still used in most applications. Is there a reason for it? So I'll pass this over first to Kurt, and like to get your input on the question. Kurt, go ahead.
Well, I think in regards to the quarterly surveillances or inspections that are done, I mean, that's a recommended practice that comes right out of IEEE 450 for vented lead acid batteries. You know, there is also monthly recommended practices, and then if you get into you know, nuclear power plants, you know, there's surveillances being done on a weekly basis, and that's really to satisfy more of their what they call their tech spec, or their licensed tech spec compliance. But the quarterlies are very important, because if you look at the IEEE 450 standard, and again we're talking about vented lead acid batteries, it's, you know, there's float voltages taken, specific gravities, you know, so you're looking for state of charge, you're looking at, you know, basically the condition of each individual cell, and then again the condition of the overall battery string. I know a lot of end users, you know, are satisfied with doing quarterlies as a minimum. And you know, that is a good start.
Okay, thank you, Kurt. Curtis, do you have anything you'd like to add?
Yes. So this quarterly thing, like like Kurt mentioned, in utilities, they actually do maintenance more often in certain types of generating stations. However, the quarterly thing is most common in data centers. And obviously battery monitoring is most common in data centers too, at least it has been in the past until the NERC order, and we might talk more about that later. But my personal opinion, and this is what I tell people who own data centers and UPSs, is if you install a battery monitoring system, you can take your quarterly maintenance down to annual. That's not in any standard that you'll find anywhere, but battery maintenance systems are costly, and so why did you spend all that money if you're going to continually sit there and look at the battery over and over and over? Let the battery maintenance system do most of your work for you, and then every year come in and verify that the battery maintenance system is reading correctly, so you can take a portable test set and to check your readings, essentially. Make sure that you've got good connections and that type of thing. So that's I don't know why users stick to the quarterly. It might be that, like Kurt said, because it's what they've always done. It's hard to change old habits, and but I would definitely recommend that if you've got a permanent battery monitoring system, you can lessen your maintenance. Don't get rid of it completely, but lessen it.
Rick, can I make a comment?
Yes, go ahead, Leslie.
Well, I agree with Kurt and Curtis. However, I would like to make the comment that visual inspections are still very important. And you could have a leaking cell if it's a wet cell, just as an example. And let's say the bottom of the jar was leaking from a bad installation or something. And if you don't walk through that room until once a year, you could have the electrolyte out on the floor and a cell with the level down below the plates. So I would disagree here a little bit, that I think visual inspections are critical on a quarterly basis.
Okay, Curtis?
Yeah, just a quick follow-up. Leslie's right for vented batteries. Visual inspections don't do a heck of a lot for you on VRLA batteries. So we're both right.
Yeah.
Okay.
We're in agreement. Yes.
Great. Now, this is the second part to this two-part question. Would you recommend battery monitoring systems that control and or regulate each battery voltage over the BMS that's over other BMSs that only monitor? And let me throw this right over to Curtis, and then we'll get input from the other panelists as well. Go ahead, Curtis.
Back in the early 90s, there was a famous paper put out by some Bell Labs electrochemists called The Never-Ending Pursuit of Float Voltage Uniformity. Because voltage is cheap and easy to measure, and anyone with a voltmeter can do it, people think that it's important. I will tell you that on a lead-acid battery, float voltage is almost worthless. There are certain critical minimums that you have to be careful of, but for the most part, it's almost worthless. Steve Clark wrote an excellent paper at BATCon 2015 that explains the reasons why trying to force voltages to all be the same in a lead-acid battery is, at best, a waste of money. That said, some of the companies that make battery monitoring systems that also control battery voltages and equalize them make good battery monitoring systems. And what I recommend to people is that they simply turn that feature off, which is fully capable in the two manufacturers I'm aware of. So you'd find pretty much uniform opinion on this panel, in spite of the marketing hype, that with lead acid batteries, controlling float voltages so that they all look the same can actually mask problems rather than help. But that said, BMS is an interesting term because, and I wanted to make this point, battery monitoring systems, as we've traditionally known them, are not the same as a BMS, a battery management system, on a lithium-ion battery. And I'd like to get away from the term BMS for a battery monitoring system and leave the BMS to the lithium ions and those types of batteries that need float voltage uniformity. They actually have to have it. They have an internal cell balancing circuit. So if it's not a lead acid or a NiCad, yeah, you need to equalize all the voltages, but it's built into the battery management system.
Okay, very good, Curtis. Now, I know Leslie's got definite opinions about battery management systems on lead acid batteries, so I'm going to pass it over to her for her comments on BMS.
Well, I just have a few that Curtis was talking about. Really, it was based on the lead calcium batteries, which is most of everything that are utilized in standby nowadays, not antimony. But, Dr. Dave Fader's paper about the pursuit of this voltage balancing or voltage matching, it's been proven that, the voltage, float voltages do not necessarily correlate to capacity at all. And as long as the cells are floating, within the manufacturer's recommended range, which means you can have a cell, as long as it's above the critical level that the manufacturer has published, it can still perform well over 100% or better than the other cells in the string. So within the industry, it is fairly, this is known, but also people, or there's been some myths that if I could keep the voltages all exactly the same at 220 or 225, then my battery will be fine. And that's absolutely not the case. And I think Kurt probably has some comments here.
No, I wholeheartedly agree with you. I mean, there's some industries, and again, I'll go back to the nuclear power plants where they have criteria that says voltages have to be within a certain range on a safety-related battery. I think the telecom market, and Curtis could correct me if I'm wrong, but back in the day was very, paid a lot of attention to what the individual cell voltages were, and that probably was more because when lead antimony was the predominant technology. But the last point I guess I'll make is that, trying to regulate the cells with some of these features that are being offered out there commercially, you have to be very careful, because essentially what they're doing is it's shunting float current perhaps away from a higher voltage cell in an attempt to bring a lower voltage cell up. And I think Curtis mentioned, it's like putting a Band-Aid on a potential problem that you might have out there if you have a cell that's starting to degrade in performance, and it's potentially starting to have internal shorts and the voltage is starting to lower on it. So you really want to be able to see these things and not have it masked.
Okay, very good. Thank you all for your responses to that question. We're going to shift gears a little bit here and move over into the safety and regulatory equipment arena. And here's the question. Is there a simple way to determine if a control house or other area requires an active ventilation system for hydrogen gas? Many control houses, especially older ones, are very leaky with regard to air and gas. Or is this issue moot due to regulatory requirements? Kurt, you want to go for this one?
Well, ventilation in a control building, say for a substation application, is very important. I mean, let's face it, the battery can and will generate hydrogen, particularly when it's on flow charge, but more specifically when it's on high rate charge. And ventilation systems are put in and are designed to move the air so that we can keep the accumulation of hydrogen below the lower explosive level, which is 4% by room volume. It is important to have exhaust fans, in my opinion. And, we see more, in the old days, most control buildings had, continuous duty fan motors, and they ran continuously. Today now there's kind of a push to, if we can intermittently run the ventilation fans and still keep our keep hydrogen levels below allowable limits, and perhaps starting those fans when the battery is put on an equalized charge or a high rate charge, or putting in a permissive that if you have hydrogen detection and if you reach a low level alarm, that will start the exhaust fan.
Okay, very good. Thank you, Kurt. And let me just get my place back here on the sheet. Curtis, you have anything you'd like to add to that?
Absolutely. So the question asks, is there a simple way to determine it? And there is. The IEEE Power and Energy Society Resource Center contains a very simple spreadsheet program It'll cost you, if you're an IEEE PES member, it will cost you nothing. If you're not an IEEE PES member, it will cost you around $20, if I remember correctly, for this simple spreadsheet calculator. The spreadsheet calculator is based on IEEE 1635/ASHRAE21, which is based off manufacturer data, and it will tell you exactly how much hydrogen you're going to release in float mode and boost mode. I shouldn't say exactly, approximately. And you'll find that the amount is very, very tiny. So while you do need an exhaust fan, you don't need a very big one.
Yeah.
And to the point about them being leaky, the reality is that in most buildings, above ground buildings, if it's not buried, if it's an above ground building, it probably doesn't even need an exhaust fan. But that calculator will tell you how much gas is approximately going to be produced and what the CFM is and how big of a CFM fan you need. And I'm talking less than a CFM in most cases for a control house. It's just teeny, 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 tiny, even on boost charge or equalized charge.
And could I just make a comment? Curtis, is that the calculator that you put together, you created based on IEEE 1635? That's
correct. Yep.
If I could make a comment as well. Curtis, the last time we met for an IEEE meeting, you made a reference to if the air exchange is set up for human occupancy, which I believe is 1 CFM per square foot, then you would also meet the ventilation requirements for the battery room.
Actually, that's way higher than human occupancy. 1 CFM per square foot is like, that's the fire code default if you don't run calculations.
Okay.
And so human occupancy typically ranges, and it depends on which model building code is being used and which local building code, but typically ranges from anywhere from 2 to 12 CFM. I mean, 2 to 12 air changes per hour, sorry, ACH. And if you run those calculations, it's about 40 to 400 times what you need to get rid of the hydrogen coming off the batteries. It's just tiny amounts. Everyone has a war story that they've heard about a hydrogen ventilation event where it came off the batteries and ended up exploding. Almost all of those took months and months and months in sealed rooms with batteries in thermal runaway, the air conditioning shut off, all of those kinds of things. It's just, can it happen? Yeah, but you really got to abuse the heck out of the batteries to make it happen. In fact, hydrogen, and this will answer another question later on probably. You don't even need IEEE 1635/ASHRAE21 does not require you to have hydrogen detection, nor do any of the fire codes or building codes. They do not require hydrogen detection because the amounts produced are just so small.
Yeah, I know in 855 there's a mention about connecting it to the exhaust system, but you're about air exchange, not necessarily about detection.
Right, and it's an option for detection. It's not a requirement.
Right.
Okay, very good information there. Thank you all for your comments. Moving on into inverter and UPS area. How will I know what size UPS battery I will need? And Leslie, would you like to start the discussion with that?
Sure. So, well, you know, that question really is dependent upon your system and what your specifications are. But just how a UPS battery would be sized is, you know, of course, we have to know what is the duration, the backup time we're looking for. We need to know the size of the UPS and the kWb of the battery. If we don't know that exactly, although the UPS manufacturers generally can give you that, you have to know the output kVA of the UPS and then the efficiency and the power factor to work backwards, because, you know, the battery's got to give a little more power or energy to the inverter that then inverts it to AC for for the output. So we need to know the voltage window that the inverter is going to operate in so we can determine the number of cells and the end voltage. Today there has been, typically the UPS application was 15 minutes, but in the past 5, 7, 10 years, there's been a push to drop.
Looks like Leslie's connection is having some technical difficulties there.
I'll follow on with where she was going if you want, Rick.
That'd be fine, Curtis. Go ahead, please.
Yeah, so what she was basically saying is there's been this move towards 5-minute backup times. And that's at full UPS load. Many UPSs are nowhere near fully loaded, so they'll actually last longer than that. But so yeah, you've got these 5-minute loads. IEEE 1184, which draws on, it's the IEEE standard for UPS batteries. It draws on IEEE 485, which is the sizing standard, but it contains some really good examples in Chapter 7 about how to properly size, just going through all the things that Leslie was saying. And just so people are aware, because there's a later question on this, so we can cover it now and not have to cover it later. Many people are starting to see more and more lithium-ion batteries in new UPSs. And those lithium-ion batteries, oftentimes the manufacturer sizes them, but the new version of 1184 that'll come out next year will have an example for lithium-ion sizing in addition to the lead acid and NiCad sizing, and nickel zinc. It'll even have a nickel zinc section.
Rick, if I may add one thing, and Leslie was alluding to some of the parameters you need to be aware of, and one that's very important is the end of discharge voltage of the battery, to size the battery properly, and that's going to typically be based on what the minimum operating voltage is of the inverter of the UPS. And I might add too that most of the major battery, that is vented lead acid and valve regulated lead acid battery manufacturers, have sizing programs where you can, calculate or determine the size of your battery based on a constant power load. And Leslie mentioned knowing the kWb, which is in other words what the constant power of the battery requirements are. So that's something that's a handy tool for you.
Okay, very good. Yeah, there are a lot of factors that play into correctly sizing any battery, whether it be for constant power or constant current. And I was somewhat distracted here with something else off to the side here, but I don't know if voltage drop was mentioned between the battery and the input to the inverter or UPS. I've been personally involved on a couple of jobs where runtime was not met, and we found out that we had 6 volts of drop in the cabling between the battery and the UPS, and they had to make adjustments at the UPS for this system to work. It was either that or replace thousands of feet of cable, the latter of which just isn't practical. So it turned out that the inverter could be dropped to a lower voltage to accommodate that. But had that not been the case, somebody would have been paying for new cabling to reduce that voltage drop accordingly. I wanted to go back to briefly the discussion on ventilation. And Curtis, could you just repeat the IEEE document number for everyone that calculator is sized to? I believe it's 1635, but I'm not sure.
That's correct. So the IEEE document is 1635, and the ASHRAE, it's a joint sponsored document with the American Society of Heating, Refrigeration, and Air Conditioning Engineers. The ASHRAE document number is 21. You can buy it from either ASHRAE or IEEE. The document actually costs you more than the calculator. I talked about how the calculator on the PES Resource Center will simplify everything for you. It won't require you to read the whole document and run the calculations by hand. It'll just let you input the appropriate data and run your calculations. Many of the battery manufacturers in these battery sizing programs that Kurt was talking about will also give you the gas generation in their battery sizing program, which is wonderful too. So that's a free program that's on their website. You just have to ask for a login for it, and which they'll happily give you.
Hey, Curtis. Curtis, this is Christopher. One more time. I'm sorry. I was trying to type those numbers down. Could you repeat that one more time? Those documents.
Yes, IEEE 1635 and ASHRAE 21.
Thank you, sir. Go ahead, Rick.
And when you go to the PES Resource Center and you're looking for the calculator, look for battery ventilation, and you'll find the calculator.
And could I just make one advantage to the calculator is that you can change your parameters, like when the battery's on equalize or float, or if I'm going to be operating at 85 degrees normally rather than 77. So as a designer, you can get a range of what the hydrogen evolution might be and design from there.
So along those lines, to Leslie's point, I'll put in an advertisement for BatCon. Assuming we have a BatCon here in May 2021, if you'll attend BatCon, I will have a video explaining exactly how to use that calculator and show the examples of how you change the values. Haven't made that video yet, but I will have it.
Okay, very good, Curtis. Thank you. And yeah, I think everything's still well up in the air about the upcoming conference in May. And just as one brief comment about battery sizing applications, they used to be software on compact discs or DVDs, and now everybody's moved into the cloud. So this is all online stuff, which of course requires an internet connection, but information can easily be updated, changed as necessary, and I think it's definitely a better way to go for everybody, because you can get updated information next time you log in. We're going to talk a little bit now about lithium batteries and lithium battery installation, and I'm going to read off the question, but I'm going to pass it right to Curtis. Can you describe how NFPA 855 will affect the deployment of lithium products in data centers, utilities, telecom, and telecom type applications?
Yeah, so let's talk about NFPA 855 just a little bit. NFPA 855 is a brand new quote unquote code issued in 2020. Code adoptions, model code adoptions like NFPA 855 take years, and so your jurisdiction may not adopt it for a while. Many jurisdictions in New York have already adopted it. And NFPA 1, which is one of the model fire codes, the 2021 edition will just point to 855 for battery requirements. IFC the International Fire Code is being modeled to look like NFPA 855 in the battery requirements. And the big deal with both the IFC and NFPA 855 with lithium-ion batteries is that you have to space them. So one of the big advantages to lithium-ion batteries is space and weight over lead acid and NiCad. However, if you look at some of the offerings from the various UPS manufacturers, what you'll see, if they'll open the cabinet doors for you in their pictures, is you'll see a half-empty cabinet. And the reason is because they can't put more batteries in that without exceeding the maximum that's allowed by NFPA 855. And the reason for that is lithium-ion batteries are somewhat more dangerous. They can produce a bigger fire than other battery types, and they have produced a lot of fires. Not necessarily in the UPS market yet, but definitely in other markets like telecom and energy storage, they've produced a lot of fires. And so the NFPA 855 and IFC require you to space 50 kilowatt hour modules 3 feet apart. So in the end, you save exactly 0 room. And in fact, I've run some calculations where the lithium-ion battery installation for a UPS takes 6 times the space that the lead acid battery installation. Definitely weighs less, but it takes less space. Or it takes more space.
Okay.
I have a visual on the summary of that. You want to pass the screen share to me, I can put that up on screen.
Okay. Christopher, can you pass the presenter to the presenter rights to Jeff for that?
Okay, here we go.
There you go.
All right, so this is what was mentioning. This is a summary on the first revision of NFPA 855 group spacing, and he was saying 3 feet from other groups' walls. The interesting thing about this is that when talking with some of the specifying engineers, they actually interpret this as being 3 feet around each cabinet, which means that they're interpreting it at this point as the 3 feet can't be shared. And so now they're saying, well, I have to leave 6 feet. And be the intent, but that's what's being discussed. And then, of course, you have some other spacing requirements. 15 feet between cabinets and intakes that would lead back into the building, 10 feet for fire egress and things of that nature. So I don't know if you want to comment any more about this, Curtis, while I have this up.
No further comments other than the fact that it seems to be 30 to 40% of the market share of new UPSs is lithium-ion batteries. The big problem is that in the many environments where they're going, where the NFPA 855 or IFC latest edition have not been adopted yet. By those local jurisdictions. NFPA 855 is the first code that I know of that doesn't allow grandfathering. In other words, the AHJ has the ability to come in and, let's say in 2025, your local jurisdiction adopts NFPA 855 and they walk into your facility, they have the ability under that code to say, this is unsafe. You're now required to space everything 3 feet apart and 3 feet away from the walls. So that's a big issue. Whereas historically, when you look at fire codes and electrical codes, you're grandfathered until the next time you do major work in there. This one, they have the ability to override the grandfathering, the AHJ does, and that's a big deal.
That is.
Curtis or Jeff, could I just make a comment though? This does apply or maybe doesn't if you have passed UL 9540A testing, right? Does the spacing can be reduced, correct?
Okay, so very good question. And that was brought up by one of the questioners and the questions that they put together for us. And the answer is maybe. So UL 9540A is not a pass-fail test. So let's not get confused between UL 9540, which is a pass-fail test, and UL 9540A. UL 9540 is for energy storage systems, the whole system, not just the batteries, but the whole system. And it's a listing. UL 9540A is a fire test where they actually put everything on fire and try to force they do force the batteries into thermal runaway, and then they measure the heat coming off it. And if all it does is give you the amounts of heat and the amounts of soot and fire and all that kind of stuff. And so what's going to happen is you can show the results to the AHJ and they can allow you to lessen the distances. There is not a single lithium-ion battery that I know of that's been through UL 9540A testing that shows decent enough results to where an AHJ is going to give you any relief. There are other battery types that have been through UL 9540A where they're going to give you sometimes relief from the 3-foot spacing, such as a sodium nickel chloride, but a lithium-ion, all the fires have been so bad that nobody's going to give you relief.
Okay.
All right, very good. Any other comments before we move on to another lithium question? This goes under sizing and selection, primarily selection. There are many different types of lithium batteries. How do you know what is the safest with integrated battery management systems, of course, to support a substation and will communicate to a central office when there is a problem and not burn down your substation control house.
I'll take the first crack at that and then
Okay, go ahead, Kurt.
turn it
Yeah.
over to Curtis. There's many different technologies or chemistries of lithium-ion batteries, and I think that's something that needs to be looked at and evaluated for the application. And I saw substation in here, so I think maybe that's why I jumped in first. The iron phosphate chemistry is probably, I'm going to say, perhaps maybe the safest because it's the most thermally stable of the chemistries. Curtis might disagree with me here, but the other chemistries are mostly metal oxides, and they operate, they float at a higher voltage. The iron phosphate, it gives you a little less energy density than perhaps, and power density than the metal oxides. But that might be one chemistry that could be looked at. And of course, then the evaluation has to take place to make sure that fire codes are met. You have proper fire suppression, and as far as communicating, through SCADA or something like that, the lithium-ion batteries do have the battery management systems that we talked about a little bit earlier, and there's a lot of communication that can take place between the battery to SCADA to give you warnings if something is going awry with the battery. Curtis?
Yeah, so I agree with what Kurt said, that lithium iron phosphate is safer than most of the commercial chemistries. And it is less energy dense, which is why you don't see it being used in cars and things like that. But if you go down to Home Depot or Lowe's and buy yourself a portable power tool with lithium ion, they're using iron phosphate. And it's for the safety reasons when you're dealing with the consumer market. So phosphate is a safer chemistry. Titanate is the safest chemistry, but it's way less energy dense, and so hardly anybody is using it, at least in the applications we're talking about. But it's by far the safest of the lithium chemistries. Speaking of safety, though, we've talked a little bit about UL safety testing. Even if you're using an oxide technology like LMO, lithium manganese oxide, you can have a relatively safe battery by design, and a lot of it has to do with, you can't prevent thermal runaway of an individual cell. It's going to happen. 1 in 10 million manufactured cells on average are going to go into thermal runaway. What you can work on as a lithium battery manufacturer is cell-to-cell propagation. So if you design the battery properly, you can prevent a tiny fire from growing into a huge conflagration. UL 1973 first came out in 2013 or 2014. It did not have cell-to-cell propagation testing for lithium-ion batteries. Edition 2 came out in 2018 and has cell-to-cell propagation testing. UL 9540 for the battery energy storage systems has cell-to-cell propagation testing. So make sure that whatever battery you buy has passed UL 9540 or UL 1973 second edition or later. If it has not passed that, you run the risk of a big fire as opposed to a little fire.
Very good point.
Okay, very good. Thank you both for that input. Okay, so this is a question on battery monitoring. It does not address, it is not addressing a specific electrochemistry. It could be for lead or it could be for lithium. But the question reads, which BMS requires the least amount of maintenance? So that could be construed as battery monitoring system or battery management system. And I'll throw it over to Kurt initially. I think you could address something with regard to PRC5 on this for the utility folks that are logged in today.
Yeah,
Maybe we can
and
look
that,
at some other parts of the user community as well.
yeah, absolutely. Thank you, Rick. So I'll address the BMS, meaning battery monitoring system, for this question. And you know, as it relates to utility applications, yes, we're starting to see the utility industry move more towards battery monitoring in substation applications, and in many cases that is to perhaps comply with the NERC PRC 005 standard, and you know, to, I guess the end game really is to improve the reliability of the bulk electric system, and part of that is to make sure that the battery is not degrading and can perform as designed. So battery monitoring systems, it's important if you're using it in a substation application to make sure that the parameters that it measures are, you know, agree with what PRC 005 is requiring, which is going to be cell voltages. You know, you've got ohmic testing, if it be internal resistance or impedance or conductance testing. We call that ohmic testing to combine the three technologies together. But and most commercially available battery monitoring systems have that capability. You know, there's float current measurements you can make or take. I've found that something that's really important, and again required by PRC 005, is the intercell connection resistance, and a very important measurement to take. EPRI years ago came out with a study that showed that over 90% of battery failures were the result of degraded or very high resistant intercell connection resistances. So you know, to have a BMS that can perform the intercell connection resistance, you know, to me is very, very important.
Agreed. Okay, very good. Having had some background over years with a particular battery monitoring system or range of products from a given manufacturer, the question that always came up from folks who had already had their systems installed, commissioned, and operating, how often should I calibrate this monitoring system? And can I do it myself? And the answer to the latter question is generally no, you can't calibrate it yourself. And I think that may well apply to a number of other battery monitors that are out there or that may show up in the future. Now, a lot of these things are basically self-calibrating or require no calibration after they've been installed and commissioned. But while I'm thinking about it, it is a good idea, I think has already been alluded to, that you need to look at the data that the monitoring system is gathering and do the trending of that data so you can determine whether or not there is a problem with that battery from the recorded data, or if there is data being recorded that looks just totally out of place, then you might step back a step or two and say, well, maybe there's something going on with the monitor. Like, oh, we always get this really high reading of intercell connection resistance on this one connector. Well, on one side, we could say, well, the connector probably is loose or corroded, or maybe there's a loose wire. Or if it's reading infinite, there may be a broken wire. That's one thing about battery monitoring systems in general, whether it's lithium, lead acid, what have you. There's a lot of wiring harnesses on these things. And if somebody is not careful cleaning or doing maintenance or repairing connections, they can break wires or not reattach wires, et cetera, et cetera. And that becomes more of an issue if there's just a lot of people, you know, basically working on the battery, cleaning the battery and so on. But really is important to look at the thing and make sure it's actually working, and go look at the data, you know, maybe once every couple of weeks, once a month, depending on how frequently it captures the data. And you know, just because there's a little green light on the front panel is not necessarily indicative that the thing is working. Any other comments from anyone else on the panel before we move on?
Curtis.
Yeah, so the question was, which one requires the least amount of maintenance? That was what the questioner wanted to know. And to Rick's point, they all require maintenance. And my experience with the 9 different major manufacturers of battery monitoring systems for lead acid and NiCad is that you're going to have to maintain all of them. There is no magic bullet. You can't just hook it up and forget it. You have to go out, like I was saying, once a year and verify that your readings with a handheld meter, verify that the readings of this thing are giving you are good. It may not, as Rick pointed out, may have a green light on it, but it might be giving you a bad reading because there's a loose connection. And so anytime you're dealing with electronics, which is what we're dealing with here, a battery monitoring system is a collection of chips and boards and so forth. It's going to require maintenance, and there's just no way around that.
Okay, very good. Thank you, Curtis. Anything else? Okay, moving into lead acid battery area, sizing and selection. This question is, could you talk about the temperature correction factor for sizing batteries, and what value was recommended to be used in an ASHRAE Climate Zone 7 for batteries located in climate-controlled substation enclosures that would lose heat during an outage? Kurt, you want to pick up the first comment on this?
Well, the temperature correction is something that should always be considered in a for sizing of a lead acid battery, if it be vented or valve regulated. The issue is that as temperature decreases, the chemical reaction of the battery slows down, so basically you lose performance. So if you have and again, the batteries are all rated at a standard temperature here in the United States of 77 degrees Fahrenheit. So all the performance data that you see from a battery manufacturer is going to be based at a standard temperature of 77 degrees. Now, if you have an application where your temperature is going to be lower than that, or your minimum expected design temperature is going to be much lower, then it's important that you size the battery to that temperature, that minimum expected temperature. IEEE 485 provides a great deal of guidance on that, and the recommended correction factors based on your minimum design temperature. You can also get, if you want to be more exact, you can get that information from the battery manufacturers. But I think again, temperature correction is very, very important, particularly in areas that are quite cold, and even if you have an environmentally controlled building, there is probably going to be some minimum expected temperature that your ventilation and heating system is designed to be operating to. So it's something that's very important, because you want the battery to be able to perform its design function at the coldest expected temperature.
Curtis, you have a follow-on for that?
I do, because the questioner asked about Climate Zone 7. So I looked up ASHRAE Climate Zone 7, and that's southern Canada, which, of course, is plenty cold, especially in certain parts of it, especially if you get in the mountains or whatever. Mm-hmm. So the caveat that I would take to that is, don't assume worst case from climate data, because remember, you're dealing with a building that was heated just right before you went on batteries. And so if I looked up the worst case, For example, at minus 20 C in southern Canada, I'd need to oversize my battery by 300%. If I were using the correction factors out of IEEE 485. But I don't really want to do that because it's a waste of money. So I would talk to my ASHRAE trained engineer, my mechanical engineer, my HVAC engineer, and I'd say, okay, how fast is this building going to lose heat?
Right.
If I've got a 3-hour backup and I'm only going to lose 10 degrees C from 25 C in that time period, there's no reason for me to size the battery for minus 20 C. Minus 15, or 15 C might be perfectly fine in that case. So don't go overkill on this sizing factor. Realize that you're coming from a heated situation and you're slowly losing heat.
Yeah, let's say that's a 1,000 amp hour battery, okay, at the 8-hour rate, and the heat goes off. All that thermal mass isn't going to chill down in a couple of hours. It's going to take a long time for that to actually get cool enough to respond negatively, if you want to use that term, I suppose, after having the heat fail. So I think you're looking at, if it were like maybe a 20 amp hour battery, that would definitely be a different situation, a lot less lead. But, conversely, a much larger battery is going to take a lot longer to cool off and probably be just fine.
The other part that plays into it is your load. If in that same control house, you have, let's say it's a 125 volt plant and you have 20 amps of load, you know right there that that 20 amps of load, that's your constant load, your base load, you know that's producing 2.5 kilowatts of heat. It has to. It's burning it up right there in the building. So you can give that to your ASHRAE engineer and say, hey, here's how much heat I'm producing. Even though the heater's not working, the equipment's a natural heater.
Now, thank you very much, Curtis. And looking at our question pool here this morning, right next door to this question is another question about temperature. So we're going to stick with this for a little bit longer, okay? But it is addressing lithium batteries. So when we look at this, the question is, what is the lithium battery temperature to ensure longest life? And that may be different for different lithium chemistries, but Curtis, I'm going to let you have at it on this one.
Okay, I'm going to ask Christopher to give me control to share the screen. I'm going to share a graph with you. We'll see. Christopher, you got that for me?
Yes, sir. I'm working on it. Give me just a moment here.
So while he's getting that ready, what I will say is that 20 to 25 degrees C, 68 to 77 degrees Fahrenheit, optimum temperature for almost all batteries, including all lithiums. Now, can you get a slightly longer life by running them a little bit cooler? Just like all batteries, yes, but that's, you pay in capacity, just like all batteries. So let me share this here. Let's see. Let's see if it'll share for me. Share. There we go. All right. So this graph right here will show up in the next edition of 1635, IEEE 1635 / ASHRAE 21. You can see the optimal temperature there between 20 and 25 C. You can see NiCad, VRLA, vented lead acid here at the top that shows where you can operate them. These arrows on either end, so here you have NCA, Titanate, LMO, NMC, LFP, and LCO right here for lithium ion down here below the dashed line. So these are all your lithium ion chemistries. The arrows basically show that you taper off charging and discharging in those temperature ranges. The battery management system says, nope, I can't allow you to charge at full rate or discharge at full rate at those temperatures. So they have a fairly wide operating temperature range. So for example, if I have a phosphate between about 18 C and 50 C, most of the phosphate chemistries will allow me to fully charge and discharge it. But if I get below 18C, for example, the BMS is going to control that charge and discharge and taper it. So I'm not going to get full capacity out of it or recharge very quickly. So once again, best life right here at the optimal temperature range, but there is a range that you can operate it and still get full charging and discharging. The key to it is that except for LTO, most of them are nowhere near as good as the aqueous technologies as far as the width of the range. So if you're dealing in an uncontrolled environment, you might not want to use lithium.
Okay, very good. Thank you, Curtis. Any comments from anyone else on the panel? Okay. Lead acid batteries it's under design and specification, but it really has to do with installation. And it looks like everybody's going to have something to say on this. The question is, what tests would you recommend when installing a new battery system? Let me start this off with Leslie, and we'll move about the panelists because it looks like just about everybody's got a comment on this, which is not surprising. So Leslie, go right ahead.
Okay, well, with VLA, vented lead acid, of course, and this is based on IEEE 484, which is the installation document, and also 1188, I guess, or is it 87 for VRLA. But, you know, you need an initial acceptance test once it's installed, or perhaps you might do it at the factory. This is for lead. And I think that's critical. It's a commissioning charge. It gives you a baseline capacity that from that point on, you can then trend the capacity of your battery with the regular performance tests that are recommended from that point on. But that's just tests. And I'm not sure from the question, we don't want to forget about installation data, how critical that is to have your baseline connection resistances, you know, gravities to make sure the cells are all fully charged and you have the right gravity, float voltages, and for VRLA, of course, you want to get internal ohmic readings only during installation or initially on installation, but that's not your baseline. That's just to find infant mortality. 6 months into service after the battery's been on float charge, then you get your baseline internal ohmic readings. So.
Okay, very good. Kurt, any additional?
Yeah, Leslie brings up a good point about, getting the initial data, because that is so important. And it has to be, records that are kept for the service life of the battery, because, everything you're looking at the battery, you want to trend. And, if you're doing a capacity test, and again, a capacity test, or in this case on a new battery, it might be referred to as an acceptance test, but you're testing it at a published rate. And that's to make sure that the battery was delivered and installed and can deliver the rated capacity as stated by the battery manufacturer. And that's really kind of your starting point. And you're going to trend capacity if you follow the schedule of IEEE 450 for vented and 1188 for IEEE standard 1188 for valve regulated. You're going to do that on a 5-year basis. But everything else Leslie spoke of is important, and it's all about the data. And you want to make sure that you've got good data, and you want to be able to trend that. So, the other thing I guess I might add, and I know everyone else is going to have something to say on this, is very important. It is for the warranty on every battery manufacturer is going to ask you, okay, I want to see your initial charging records and what testing did you do after you installed the battery. Yeah. And they're going to want to see what subsequent tests are if you're doing it on a quarterly basis and things like that. So All that is very, very important.
Okay, very good. Totally agree with everyone on that. Curtis, do you have something you'd like to add?
Nope, I've talked enough for a while.
Okay.
What they said is great.
Okay. Jeff, anything? You need to unmute.
Sorry about that. Yeah, I'll just add one thing. Great comment about letting the battery settle down before you take the baseline readings. But I've also think it would be a great idea to Kurt's point about readings. I know in the past I've actually caught myself a few times where the washers are placed in the wrong spot in between the post and the strap, and so having some sort of strap resistance reading after or resistance reading after the initial installation before that battery goes into service would be a really good idea to catch those kind of problems.
Mm-hmm. I want to just say one other thing about an initial test before even commissioning the battery into service is once you've installed the battery and you've done all your inner cell connection, you've torqued everything, is taking the open circuit voltage of the battery string, because I've seen, I think everybody can attest to this, where a cell was put in reverse polarity, either by the way it was installed, or we've actually seen them come from the plant where the plates are put in backwards, and so even though it says positive on the post, it's really negative.
Mm-hmm.
Yeah. You can have that, and you can also have an installer just inadvertently place the cell in reverse polarity and just put it in the string wrong.
Mm-hmm. Right.
And for our attendees, if you do have a cell that is in reverse polarity, your open circuit voltage is going to be off by not 2 volts, but it's going to be off by 4 volts. So if you figure that your open circuit voltage is, let's say, 2.05 average, and you multiply that times the number of cells in the battery, and what you measure is off by 4 volts, you got 1 cell in backwards, 2 cells in backwards, 8 volts, 12 volts for 3 cells, and so on. So that's a really easy way to check to see if you have anything in reverse, without necessarily examining physically every individual cell, but you can do that as well. Leslie?
Yeah, so Rick, that's a great point, and Kurt, that addresses installation concerns. But you also would like to get open circuit voltage of every cell or unit as you're installing them, or once you've got them installed, just so you know that each unit is at approximately the same state of charge, because that's what open circuit voltage will tell you. You don't want to mix cells that have been on the shelf, for a year in with cells that are, shipped fully charged from the factory. Or you just may need to do some special, initialization charging to accommodate that. Mm-hmm.
And you'll find, Leslie, if you do that open circuit voltage test on each cell, that and you're right, that lets you know that you have a cell that's at a full state of charge, and that can oftentimes be used in lieu of taking a specific gravity measurement.
Absolutely.
So,
yes.
If you have a nominal 1215 specific gravity, the general rule of thumb is you take the specific gravity plus 0.845. So in reverse, if you take your open circuit voltage and you subtract 0.845, and this is for a 1.215 specific gravity vented lead acid battery, that will be about what your specific gravity is of the battery, of the cell.
Okay, very good. Well, let's move on to another question. Also in the world of well, this isn't actually installation, but we're going to talk about lead acid batteries again. The question is quite simple, short and sweet. What is the lifespan for lead acid batteries? I can give a short and sweet answer. 2 words that we all love to use: it depends. But there's of course more than just it depends. Okay, next question. We'll go ahead and let the panel go after that. And Leslie, let's start with you on this.
Okay, well, I'll just address, vented lead acid flooded cells. And, again, it depends on the model of the battery, the application for which it was designed or optimized. So for a high rate application, UPS data center type application, wet cells, thin plate wet cells optimized for high rates. Typically, I would see 8 to 12 years life. For telecom applications with very thick plates, optimized for 8 hours, let's say, I would definitely expect to see 18 to 20 years. And I can mention, I know many cases where they've been in service for 24, 25 years. So it does depend upon the application for which the model was optimized, and then somebody else can address VRLA.
Okay, Curtis, you want to go after VRLA?
Sure. So there's really two types of VRLA. There are 2-volt VRLA, what they call 20-year design life, and that has nowhere near what they'll get. And then there are monoblock VRLAs that come in different design lives. The monoblocks or multi-cell jars, like your 12-volt, 6-volt, so forth, come in different design lives. You see 5-year design lives for the really tiny ones, 7 to 8-year design lives for some of the tiny ones that are longer life, and then 10 to 13-year design lives for some of the 12-volt stuff.
2-volt.
Well, the 2-volt is 20-year design life.
Yes.
Yeah, and but the 20-year design life, depending on the model, as Leslie's saying, and the manufacturer, assuming that you're in a decent temperature environment, 20 to 25 C, depending on the model of manufacturer, I would expect to see in a utility or telecom application, I would expect to see 7 to 15 years. 15 being the very, very top end. Yep. And in a UPS application, I would expect to see 7 to 9 on the 2-volt VRLA, from the very best of them. On the 10-year design life 12-volt monoblocks, you can, with some of the newer designs that are out there, high temperature designs and so forth, you can see a full 10 years in a good environment. And in some cases, maybe even a tiny bit more. But on average, I would say for non-UPS applications, you're going to see something in the range of 7 to 8 years in a good environment. Leslie, you wanted to say something there.
No, you covered it.
Okay, so the other caveat, though, is 12-volt monoblocks in UPSs. The older the UPS and the higher the load on the UPS, the more the ripple is going to shorten the life of those batteries. And that's feedback ripple from the inverters mostly. And what's going to happen is you're going to see battery lives in the range of 3 to 6 years is pretty typical for VRLA monoblocks in a UPS. The newer the UPS and the lower the load, you can start seeing out to the 5 to 7 year range on those monoblocks.
Okay, very good. Thank you, Curtis. Let's see. Kurt, did you have anything you wanted to add?
No, I won't. Just to your point about it depends, and I heard Curtis say that it depends a couple times too, and just our industry and a highly respected colleague of ours who's got more years in this industry than me, Dan McMenamin, used to say that in our industry, we have more depends in a nursing home.
Okay. Let's look at lithium batteries again, okay? And it has to do with the operation of lithium batteries. We see numerous lithium battery suppliers pushing stated 80% SOC and warranty service period out to 10 years or more. I think that means depth of discharge, though, but it seems like depth of discharge makes more sense there. But can these batteries really be expected to cycle hundreds to thousands of times a year, for example, 10,000 to 50,000 cycles over a 10-year period without significant decrease in performance or reliability? Curtis, what do you think?
So if you think about the primary application for lithium-ion batteries today is cars, besides your portable applications for laptops and cell phones and so forth. But cars, if you think about how often those cycle, and they're really expecting, in the longest lived lithium cars have been out there for well over 10 years now. And so it is not unexpected to see, if you think about if you daily cycled, that's 365 cycles in a car. So if I'm doing, 10 years, that's over 3,000 cycles, and those are deep discharges if I'm running for any decent amount. The way that cycling works for all batteries is the number of cycles is related to the depth of discharge. So if I have 5,000 cycles at 80% depth of discharge, I might get 20,000 cycles at 40% depth of discharge. And so at 10% depth of discharge, it would not be uncommon to see 100,000 cycles. Now, do I expect degradation? Absolutely. But how much degradation? Unlike a lead acid battery, the capacity of a lithium ion doesn't drop off a cliff when it reaches 80%. And so you can easily run them down to 70% capacity, 50% capacity. There's a lot of talk about repurposing batteries out of cars and using them as second life for energy storage systems, because when you pull them out of the car, maybe they have 70% capacity left. And I can continue to use them because they're not dropping off a cliff in their capacity, and continue to use them after that in maybe an energy storage system. So yes, is there degradation? But yes, it's a slow degradation by cycling. The same thing applies to a float application. In a float application, yes, the constant float is going to beat on the battery chemistry a little bit, but it's a slow degradation. And once you reach 80%, that's not necessarily the end of life. Depends on how much capacity you need.
Okay, great. Thank you, Curtis. We're going to talk about battery monitoring and maintenance. This really gets into internal ohmic measurements, whether it be impedance, conductance, or internal resistance. What is the correct reference for a battery? And I'm paraphrasing here because I'm not fully understanding this part of the question, but what is the correct reference that a battery has to be taken? So I'm thinking they're looking for what is a reference number given a particular type of ohmic measurement. What is the percent of variation as normal reference for new batteries? Leslie, would you like to start off the conversation on this one?
Sure. I think I'm going to actually address the second question, which is what is the allowed degradation, percentage of variation. So IEEE 1187, the installation document for VRLA, talks about obtaining internal ohmic readings for your cells, your valve regulated, as you are installing them. And basically you're looking for infant mortality. And in that case, the document says that you're looking for something that is greater or less than 50% of the average. And by greater or less than, that depends upon if it's resistant for greater or less than if it's conductance. So, right there as initial installation, you're looking for a 50% deviation from the average or change from the average. Now, that's not the same as during routine maintenance. In that case, we're typically looking for 30 to 50% from your baseline, but your baseline is a number that actually you should get after 6 months in service. You can ask the manufacturers for a baseline internal ohmic, but you've got to make sure it's with using the same instrument you were using. So I'll let the other panelists make some comments on this.
Okay, very good. Thank you, Leslie. Kurt, would you like to go ahead and give us a little bit of your opinion on this?
Yeah, the reference value is very important, and that's something that should be you should get from your manufacturer. And I guess I'm going to talk VRLA because any of these ohmic tests are really much more important on a VRLA than a vented lead acid battery for many different reasons. One is you can't really do internal, you can't do visual inspections of the internals of the VRLA cell, which on a VLA that tells you a lot about perhaps the condition of the battery. But the ohmic test is important, and obviously if you're seeing degradation, you're going to see an increase in impedance or resistance or a decrease in conductance. It can be argued really until the cows come home that what is considered to be what percentage change is telling you that you have degradation. Leslie said 30 to 50%. That's probably a very good number, but you just can't rely on that and say, well, I've got 30% increase in my internal resistance, therefore the battery can't perform its design function anymore.
Oh, no, right.
That's when you really have to follow it up with a capacity test.
Yes.
And this goes back to the whole thing. These tests will quantify what the capacity of your battery is. And I'll just add one other thing. There is something to take notice of too, is that when we talked about acceptance tests on batteries previously, that I think generally with vented lead acid batteries, you want, if you're going to do ohmic measurements, that baseline measurement, you want to wait for the battery to have been in service and on a constant flow charge for about 6 months before you take that first baseline ohmic measurement. So I see Curtis over there nodding. I think he's probably got.
Yeah, just one quick follow on, which is that to Kurt's point, there is no direct correlation between capacity and ohmic testing. It's a general trend, which is why when it's changed by 50%, you're much more likely to be below the 80% capacity point than you are if it's changed by 20%. So that's the general trend. So it's always best to run a discharge test. However, not all batteries is it wise economically to run a discharge test. So if I have a battery that costs $20, then why would I run a discharge test when my ohmic test tells me that it's changed by 50%? There's no reason. Right. So economics come into play, the criticality of the application. So if your batteries cost, so a lot of people use 12-volt monoblocks because they cost less money and you're dealing with smaller batteries. They often use just the ohmic testing and don't go all the way with the capacity testing, because it's not as important to them to know the exact capacity. They just want to make sure that they have some capacity and that they're not going to die if they try to go on batteries.
And I want, Rick, if I could say one more thing, I want to make a real quick public service announcement to our utility friends out there in the audience too that are using ohmic testing in lieu of capacity testing and performance capacity testing for NERC PRC 005 compliance. Just remember that this whole thing can come up if you're audited by NERC because the onus is put on you as the end user, as the owner, to demonstrate what change in your ohmic reading would constitute a degraded battery or a battery that cannot perform as manufactured, and that's kind of how it's written in the NERC standards. So that's just something to be, we can take all these measurements and everything else, but you have to do something with the data, and you have to analyze it and evaluate it, and kind of have look at the trends.
Agreed. And let's talk a little bit, if I can, to basically wrap up this question, is that the nuts and bolts of this thing, that the technician out there in the field that is using an ohmic tester, okay, we're going to make the assumption that everybody is using the same make and model ohmic tester and the same test leads, number one. Number two, Everybody has to be testing the cells. If we're talking about internal ohmic measurements, they have to be testing the cells the same way with regard to test probe or test lead placement.
Right.
One technician cannot go to the terminal posts on test like Q1 quarterly, and the next technician says, yeah, but the bolts are a lot easier to get onto, and they're stainless steel. That is going to greatly skew the internal ohmic reading by changing the test lead position from a terminal post, a nice big, if you got it available, 1-inch square post, or 2-inch post, against a stainless steel bolt or some other piece of hardware. So that is vitally important. And because, your brand X ohmic tester isn't working and you've got a brand Y, that's not going to cut it. You can't use a different tester and have any hopes of doing any trend analysis or really much of anything else except that snapshot of readings in time.
Yeah.
So you really have to make sure you're very consistent in your policies and in the technicians' training of using these instruments. Otherwise, you're just going to get garbage that you're not going to be able to make any sense of. So we're going to move on to the next question. It has to deal with safety and regulatory equipment. And here's the question. Do you see changes coming forward from UL or NFPA as new chemistries come to market that are inherently quote unquote safe? Ones that are totally non-flammable, do not cause or propagate a fire, have no thermal runaway, no explosive gases, no acid, no caustic materials under any conditions. So I guess what they're looking for is basically the perfect lithium battery. I don't know as if that is humanly possible, but I'm going to let Curtis have at it with a response on this.
Let's find my unmute button. So, and if already lithium-ion batteries are safer than they were 2 years ago, they're safer than they were 10 years ago. It's a relatively new technology in the battery world. So I already talked about titanate being the safest of the chemistries. The next big leap in lithium technology is to make the electrolytes non-flammable. So when you have a flammable electrolyte and you go into a thermal runaway situation, obviously that's going to feed the fire. So trying to get non-flammable materials into the electrolytes is where the big leap is going to come. To Rick's point, there is no battery, even a NiCad, I could theoretically drive it into thermal runaway. It's really, really difficult, but it's theoretically possible. So from a safety perspective, lithium-ion batteries are going to get better and better and better, but you're never going to have a perfectly safe battery. Anytime you store energy in a tiny box, sometimes the smoke comes out. And so we're just trying to work harder and harder to make the instances of smoke release less.
I'll ask you a question, Curtis. Even zinc air technology, that's being looked at for energy storage is not completely safe and benign.
Right. So the safest technologies, because we use them every day, are batteries that you only use once and don't try to recharge. Recharging is where all the problems come in. And zinc air is one of those technologies that is a single-use technology. It's not a rechargeable technology. And those are called primary batteries as opposed to secondary, which is rechargeable. And primary batteries are inherently safer, but even they can be dangerous. That's a lot of energy stored in a tiny space. Just like gasoline. Gasoline's a lot of energy stored in a tiny space. It can let the smoke out too. Absolutely.
Great. Well, thank you very much, Curtis. We've got another safety and regulatory question. And the question is simply stated, are battery terminal covers required by code? Jeff, can you start off the responses on that? You are muted.
Thank you. I'm going to put an interpretation out in the from OSHA, and OSHA basically has stated that any live voltage over 50 volts needs to be covered. And so you're welcome to grab that link. That's basically, how I'm making my case. But so one of the things I want to mention, though, is that I look at this in two parts. You have the intercell connectors, which is, I would say, pre-installation an issue. Basically, you can order these things pre-installation, but then there's a post-installation issue, and that's anything that's inter-tier, cross-aisle, inter-row type of cabling that happens because the cable sizes can be all different sizes. The lug sizes can be different. The orientation of that terminal plate and how the cables rest on the are bolted to the terminal plate can be in different orientations, and therefore that tends to become more of a post-installation issue. So, but to my knowledge and my interpretation of what I've been reading, it's 50 volts for the U.S., 100 volts for Canada, DC.
Can I add something here, Rick?
Yes, absolutely, Kirk.
I guess sometimes I try to look at this from a more practical side and say, I understand. I completely agree with Jeff from the OSHA compliance perspective, which is very important. But from a practical perspective, you sometimes have to look: is the battery operating as a grounded system, like you'll often see in a telecom? Although a telecom, might be a nominal 48, but operating at 54 volts, so above that 50 volt threshold that OSHA has, or more, UPS battery terminal voltages could be up, operating at 540 volts, and you may, have a grounded by design because you don't have an isolation transformer perhaps on the input of the UPS. So basically the battery seeing a ground through the AC input neutral. So you got to be real careful. Switchgear and control batteries are designed typically as floating or ungrounded systems. So theoretically, you could go up to that battery and touch one hand on any terminal, and it's not going to be a shock hazard.
Jeff, can I ask a question just for the attendees here? So how does this apply to a controlled access battery? So for example, there could be a battery room that is, only qualified personnel can enter, or what about battery cabinets where they're definitely controlled access?
Yeah, in that case, battery cabinets, that's actually considered a cover, to the system. Again, it's a lot of times based on the environment, the access to those systems. Obviously, if you have other dangerous voltage in there, you'll have restricted access, and that's arguably can be considered your restricted access. I think where this really has become more scrutinized is when you have other maintenance items for people who are not battery trained going into the rooms, say air systems or lights or anything that could be in that ceiling that they're over the systems, and then they have to worry about that.
Curtis, you got anything you'd like to add?
Just one thing that hasn't been mentioned, and this goes to the 48 volt nominal systems. It's not the intent of OSHA, nor has it ever been, to have something that floats at 54 volts or 52 volts or 53 volts be covered by the 50 volt rules. In other words, when they talk about voltages, they're talking nominal to get around that confusion. And so when we talk about below 50 volts, a 48 volt system that floats at 54 volts under the OSHA rules is not required to technically have these terminal covers because it's nominal 48 volts. The National Electrical Code has made that far more clear by getting rid of the words nominal and just using 60 volts DC. And I expect that OSHA will eventually follow. That way we don't get into the argument over whether or not it's above or below 50 volts.
Okay, all right. Yeah, there's a fair amount of confusion with that, and understandably so, especially with varying, with all the different codes and regulations that we're dealing with in this industry. Okay, we'll move on to the next question. We have discussed previously this morning, well, now we're in this afternoon. We've been discussing battery monitoring systems and their usefulness and so on. I think we've really addressed this, but the question is, are online battery monitoring systems practical? I would have to say, the short answer is yes. It is how you use them as a user. Okay, if you're the owner of these battery monitor or battery monitoring systems, how you're utilizing them, whether they're on a network connection and you're able to just grab that data from your PC or whatever device you have, or whether you're actually having to walk into the battery room to access the data. However you're using them, that's very important. I think they're extremely practical. They are not generally an inexpensive product to purchase, and that doesn't include purchase cost is covering the hardware. Then there's the installation cost associated with that. And to put battery monitoring systems in place, speaking of a practical aspect, you may well, in most cases, you're probably going to have to take the battery offline in order to attach a number of sense leads and other devices to the battery that are going to require the circuit to be broken. So it depends on what your definition of practical is. If we're talking about using them, absolutely. There's some things you have to get past on the installation of a monitor. But I will say this, don't let the ease of installation and the price tag drive your decision to purchasing a monitoring system, because that doesn't always mean you're going to get what you really need at the end of the day. So other members that got their name in the hat here. So Kurt, you want to?
I'm just real quickly, I want to say it's, they're practical. It depends, what you do with the data.
Yeah.
If you evaluate if you take the data that's given to you, you evaluate it properly, and you trend things, and yes, they can be practical.
And I would add one more quick thing, and Rick briefly mentioned the economics. Mm-hmm. Part of the economic equation is not just the cost of the batteries and the monitor and comparing those two, but comparing the criticality of lost service. So, for example, if I had a UPS system and that UPS system had 5 parallel strings on it, and then I had the same UPS system, but I had a single 240 cell string on it, and the criticality was the same, I would say that the practicality of monitoring the single string is much more important than monitoring the 5 strings in parallel. And so that's the other part that plays into it, is how critical is your system and what is the design of your system as to whether or not you want to put this on there. If your design is not very robust, monitoring makes a big difference.
Right. If I make one comment too, so many times do I see in my former life of people installing a battery monitor system, and then they do their inspections via handheld meter. And so that's always been one of the things that never made any sense to me. Yeah, these things are generally hard installed on the battery system, and then you go over it and you take an ohmic measurement over a strap or a bolt or something, and the two don't correlate. So you might be able to find a problem with your battery monitor if you're sensing something wrong there by going over and taking a manual reading. But if everything is set up right and you're getting good data, I don't see any reason to go over it with a manual device to collect your quarterly or annual PMs.
Now, there is a topic that is come to light probably more so with regard to network security.
Yeah.
More so now than ever, because every time you turn around, somebody's getting hacked. There's a security breach. And, you just kind of hear about this or see it on TV and you shake your head and go, well, how did this happen? Well, I'm not an IT guy, so I don't really know how these things happen, but they do. And I think it's important that if it's going to be a network connected monitoring system and it's going to be accessed remotely, whether it's, within the network, within the facility itself, physically within the four walls of, like I say, a data center, or probably, but more practically, would be remotely accessed from, hundreds of thousands of miles away, take your pick, but, outside the four walls of the facility, they're just as concerned about that little battery monitor as they are everything else in the data center.
Sure. Yeah.
And that, they want some assurances, that the product they're buying is not necessarily going to be susceptible to an attack from the outside. That is, if somebody can actually find the monitor. I mean, they would have to know what they're looking for to look at that, and that is very important data. So, for what it's worth, that's something that really has to be.
It's hard to get facility management and IT to work together on some of those things, but they kind of have to.
Okay. Operation. Let's see here. Another question for us. Under battery racks and cabinets, what do you expect the leading UPS backup battery technology to be 5 years from now? Curtis, what do you think?
So even though it's been trending towards, on new installs, it's been trending towards lithium ion, I suspect that more adoption of the fire codes will reverse that to some extent. The newer fire codes, that spacing requirement is going to play some havoc in the market. So I still expect it to be lead acid. And lead acid today, it's still 60 to 70% of the new installs and almost 100% of the old installs. And so even though there's been a trend towards lithium ion, I don't expect that to continue growing. It's going to stabilize and maybe even fall a little bit.
Yeah, if a lot of people still are, and of course, and will continue for the foreseeable future, be buying battery cabinets stuffed with lead acid batteries, 12-volt monoblocks, 6-volt monoblocks, what have you. And a lot of the reasons, at least from what I get from people I've talked to over the years, is, lead acid, it doesn't have the energy density of lithium, but when you look at acquisition cost, everybody looks at acquisition cost, for the UPS, the batteries, and so on. They look awfully hard at just the acquisition cost and don't really look at other things. And they say, well, lead acid batteries, they're fairly reliable. They take up more space, but hey, the check we have to cut for this UPS system expansion, for example, is going to be a lot less. Leslie?
Yeah.
Well, yeah, I mean, and the technology of lead acid is advancing with, pure lead, et cetera. So, the lifespan is better, the reliability is better. So there's no reason for, I'm in agreement with Curtis, there's no reason for lead not to stay the predominant technology, with lithium, still being used in new applications.
Yeah, I guess to sum it up, lead is not dead.
Right.
The other caveat that I would put to Rick's point about the cost of lithium ion has come down precipitously. It is almost on a par with lead acid now. It's shocking. I'm shocked at how fast it happened.
Wow.
And so I can go buy a lithium ion phosphate battery today for almost the same cost as a lead acid, including the BMS. So the cost as a comparison factor has gone somewhat by the wayside. The other technology that I wanted to mention that's being marketed for the UPS industry is nickel zinc. And the requirements on that in the fire codes are not nearly as stringent. It's treated a lot like, not nickel zinc, yeah, is it nickel zinc? Yeah. It's treated a lot like NiCad and lead acid. And so it can get some market share, but it's definitely not going to be the dominant player.
Okay. Let's see what we have here. Lead acid maintenance discussion, or question, I should say. Oh, wait a minute, maybe I skipped over one. Yes, I did, sorry. Since we're on the topic of lithium and it's become very popular, what are the current best practices for fire suppression with lithium?
So I'm actually on the NFP 855 committees dealing with that, and it's in flux. It's a new technology. So at first, what went out with lithium was clean agent suppression. So you had FM200, Novec, 1240, 1300, these clean agent suppression systems, the replacements for halon. It's been learned that that's probably not enough. You're going to have to put water on it too. And so current fire suppression technologies are a combination of clean agents and sprinkler systems, along with venting. There's two types of venting. There's minimal venting, where you make sure that you're getting rid of minor buildup, and what's called deflagration venting. Once the fire has started, you have to really vent the living crap out of it so you don't build up too much hydrogen. We talked about how lead acid batteries don't put out much hydrogen. When a lithium ion battery goes into thermal runaway, it puts out tremendous amounts of hydrogen and what's the other flammable gas? Methane. And so it also puts out other flammable gases, but those are the two primary ones. And it dwarfs the amount that any lead acid battery could ever put out. And so they have this deflagration venting. So those are the fire control strategies that are going on right now, including thermal detection in addition to smoke detection and off-gassing detection. So hydrogen detection, it's not required, but it's much more strongly suggested. The next edition of IEEE 1635 is going to strongly suggest that you put in hydrogen detection or combustible detection and possibly toxic detection for carbon monoxide.
All right. All right. Thank you very much, Curtis. We're going to move into lead acid maintenance question. And this involves the introduction of AI in this question. How do you predict lead acid battery life, vented lead acid batteries in specifically? Is there a role AI can play when trying to predict battery failures? What type of measurements are best suited when trying to predict the battery life? And I think that is a question right up there with the meaning of what is the meaning of life. It's kind of hard to figure out when the battery, in fact, is just about impossible to say, well, it's going to fail on this day or this date or in the next 3 months or the next 6 months. But the question really is asking our panel to address the question from an AI perspective. So Leslie, would you like to start off with that?
Sure. Well, AI, I just interpret that to mean what kind of data should we be looking at? What kind of trending should we be doing? With vented lead acid, well, with all batteries, again, IEEE says the only way to predict or to trend life or know where you are in the battery life is by performing capacity tests, because we've defined end of life at 80%, at least for lead. NiCad and lithium, I guess it depends upon how you size it, but for lead, it's 80% because of the drop off. So if we're trending capacity over the life of the battery by performing the capacity tests, we know where we are. And then IEEE gives you guidance on when you need to replace the battery, when there's a 10% change from the last test, or you're at 85%, you need to start planning on it. But, in reality, in practice, I think, especially like in data centers and all, your performance test will definitely give you capacity, but you definitely need to be looking at all of your maintenance data and visual inspections for VLA, because, float voltages per cell, every cell float voltage is critical. We're looking for shorting cells, because that's one of the first signs in an aging VLA battery, when you start shedding material, things like that. So to me, the most important parameters to be looking at are individual cell float voltages, float current, and temperature. Kurt, you want to add something?
Yeah, the only other thing I guess I'll add about the, using AI is that there's, there's a lot of work that's being done. I think it's Vertiv. There's some papers talk about the BATCON conference. There's some past BATCON papers that have addressed this. So those folks that are interested in learning a little bit more of some of the work that's being done can go out and get those archived papers from past conferences. There's, one other thing I'll mention in terms of, using artificial intelligence and algorithms a little bit. I mean, there's been, some work that was done, and a patent that was brought up a long time ago, a gentleman by the name of Thomas O'Sullivan, who was with Bell Labs, who was looking at voltage slope during discharge. To determine kind of what the capacity of the battery is, and hopefully to be able to predict end of life. So, there's much more work going on with that, with that type of stuff too. So, Curtis, you got anything?
No, just to follow on with that about the percentage of discharge that you have to accurately predict. Typically, it's been 100%. Kyle Floyd did a paper where he basically proved that if you take 80% of the capacity out of the battery, at least on a VLA battery, that you can accurately predict it. And all this applies to VLA because VRLA, because of the dry out phenomenon as they age, especially the AGM type and even the gel type, you cannot do a partial discharge test and accurately predict capacity because the voltage can drop off a cliff. But VLA batteries, you can do. There's, like Kurt said, there's work going on. Kyle Floyd says 80%, and he proved essentially that 80% capacity, you can predict the capacity. The work that's been done on the Tom O'Sullivan patent seems to say that 25% capacity, if you have the right algorithms and are trending that properly, if you take 25% of the capacity out of the battery, you can reasonably predict the capacity for VLA only.
Okay, very good. We've got time for one more question. We're going to be bumping up against our 2-hour mark here. So here goes with the last question on installation under safety and regulatory. How do you recommend hydrogen generation and mitigation regarding the I codes and NFA? I think that may be of NFC, possibly National Fire Code, or maybe NFPA. It might have been a type of requirements. I think we've already touched on this, but is there anything you want to add to this, Curtis?
So I saw several questions come in on the chat, so just wanted to address those in this area. So I've had very good success with showing IEEE 1635 calculations to AHJs. The fire codes, whether it be the IFC or NFPA 1, basically say, hey, you've got to calculate your gassing, or you have to use 1 CFM per square foot of floor area, one of those two. And so if you show them the calculations up from the IEEE calculator, the ASHRAE calculator, or from the document, I've never, someone pointed out they've had problems. I've never had a problem. Every single time I've shown the calculations, they're overwhelmed by the fact that you actually did calculations and the math, and they don't want to go through the math themselves. So they go, oh, that's great. Okay, you actually did the work, especially if you have a PE do it for you. That PE stamp on there is going to carry a lot of weight. So the IEEE calculations will tell you, that you can meet the codes with this much ventilation, which is typically very, very minimal. just run the calculator.
Hey, I just want to mention here that I just got a note from our host, Christopher. We have a hard stop for 12, well, in his time zone, 12:15. So we've got another 15 minutes we can go here, and we still have a lot of people on the call, which is great to see. So unless there are any objections from the panelists, let's just continue till.
Yeah, I think I can hold a bathroom break for another 15 minutes.
Okay, another 15 minutes. So
To follow on to Curtis's point, Curtis,
Yeah.
is that a generally accepted practice of 1 CFM per square foot?
No, that's
floor-
complete overkill. If you look at that, especially in environments that are not moderate climates, if you're on a cold climate or a warm climate, you're going to spend a heck of a lot of money on heating and cooling if you're ventilating at that rate. So that's why it's always best to do the calculations, unless you're in a moderate climate like Oregon coast or something like that, where you're bringing in outside air all the time anyway.
Yeah, okay.
I saw a Plante battery out in the Northwest one time that was 30 years in service, and it was still delivering a 100% capacity. But that climate had a lot to do with it. To your point,
and the fact that it was pure lead.
Yeah.
Not lead calcium or lead antimony.
Right. No impurities and very, very low flow current. So all contributing factors there. Well, this is an interesting question. It has to do with battery monitoring. It's a two-parter, and I don't think we're going to be able to probably drop names on this. We typically keep this non-commercial, but here's the question. What are the different battery monitoring systems on the market, and are they specific to a battery manufacturer? So does a battery manufacturer have their very own in-house battery monitor? So the whole panel is tapped for this one, but I'm going to pass it initially here to Kurt. Let you start this off with monitoring systems, and if anybody's making one specifically for a battery vendor, or not for a battery vendor, but as a battery manufacturer doing their own monitor.
Well, we'll talk. Let's not talk about lithium ion here, because we all know, the battery management system that's integrated with the lithium ion battery. But for vented lead acid, VRLA, or nickel cadmium, I'm not aware of any particular battery manufacturer that's making a monitor. Now, what they will furnish monitors, but oftentimes it's third party. So in other words, a battery monitoring, manufacturer is making it and perhaps maybe putting the battery manufacturer's name on it.
Yeah. When you look at the different manufacturers, the different battery monitoring systems that are available, they can be relatively simple, one string type monitors that maybe even be limited to, let's say, telecom, like 48 volts or maybe 48 and 120 volt systems. They could measure temperature in the room, the individual cell voltages, overall battery voltage. And then from there, they can just go up and become more and more sophisticated in the parameters they can monitor. For example, an internal ohmic measurement. Pick your type of ohmic measurement: impedance, conductance, or resistance, connection resistance, float current, electrolyte temperature, where there's a probe that actually goes into the vented lead acid cell. It really becomes a function of what do you think you want to monitor? What do you need to monitor? Is there a regulatory requirement for what you're putting a monitor in place for? And if so, what is that requiring? So it can get very pricey, because the more cells you monitor and the more strings in a given site you want to monitor with a monitor, some of these things can monitor up to, I believe, 10 strings of 240 cells of vented cells. that system is going to go deep into six figures. So depending on what you want to monitor is going to determine the cost. And but I agree with Curtis. With Kurt, I don't know of any battery manufacturers that are actually designed and sell their own monitor. Anybody else?
Yeah, I agree. I think you hit upon a good point that you have to look at the method of test and make sure you buy into that method of test. And if it's the a lot of times you look at the different monitors, there's definitely different methods of test and different ohmic values that you can achieve, and then of course the peripherals that you get with that. And if you're trying to do something specific, and but yeah, I don't know of any battery manufacturers who's promoting one over the other.
The other thing, there's a little different, differences in design from what, and one thing I think that's come out over the years is, one monitor may require availability of AC power.
Yeah. Mm-hmm.
Okay, others might, operate off of the battery itself, and may, so then it has to be looked at. Well, is it acting as kind of a load on the battery too that needs to be considered?
Mm-hmm.
So, and then if the monitor is relying in some respect to AC power to be able to perform, what happens when you do have a loss of commercial power? And your battery's discharging, if you lost your monitoring capability. So those are all little things you need to consider and look at.
Yeah, and I'm sorry, go ahead, Jeff.
Just saying, and communications thereof, you're communicating through the IT network, how is that, what is your requirements there as well?
Yeah, and people need to also consider not just the hardware when they're considering a monitor. And the other side of this is the software. Is it going to run on a Windows platform? That's probably, one of the most important things, since, the lion's share of PCs in business are Windows machines. But more importantly, is the software going to be easy for the individual who's responsible for collecting, trending, analyzing, and digitally printing a report or something? Is it going to be user friendly? And if it is, great. If it's not user friendly, that's when they basically go, okay, we're having terrible trouble with this software. It doesn't work real well. So what do people do? They stop using it. And that's not a good thing either. So that software has to be considered strongly in the selection of a monitor, not just the hardware and the bottom line. Okay, I got a question about inverters. And I think this will probably dovetail into a discussion about like a DC data center versus AC data center, which we've talked about historically at another conference. Is it possible to make no losses in an inverter, or can we change form using AC load to DC load and to decrease losses? In other words, I think what the questioner is asking, what about just using DC? So, Leslie, would you like to comment?
Well, UPS systems, uninterruptible power supplies, have a double conversion. So you go AC to DC. So the battery's your energy storage mechanism that's charged with DC, and then it delivers DC to the inverter, which then reconverts it to AC output. So there's two conversions. So you're going to have losses through that. If you could eliminate one of those and feed your load from DC, yes, now you've only got one conversion. So you have definitely increased the efficiency of your system, let's say. But, you have to look at, is my load equipment, can it be fed, what's the feed requirements, power requirements? Is it AC or DC? And yes, while, servers can maybe, you can get them in AC or DC input power. I know that's very common. I guess you have to look at what's more practical, what's readily available, costs and things like that.
So this, Curtis, just to follow up on that, Leslie's absolutely right. And I wanted to make a caveat about operating a UPS in eco mode. UPS manufacturer will try to sell you a UPS that's 99% efficient. It is when you operate it in eco mode, but you're also taking a risk with reliability. You're counting on the static transfer switch electronic components to transfer you over to batteries very quickly every single time, because you're not running through that dual conversion stage. And so if you run in eco mode and you have a critical load, realize that the money you're saving on your electric bill, you could lose all of that by losing your load if the static transfer switch goes bad. So that's one thing about efficiency that I wanted to get covered. The other part is, to Leslie's point, as far as power supplies. Here in the US, there have not been a lot of DC data center trials and applications. There's been a few. In Asia, it's been much more common. Japan has widely deployed 380 volts DC in telecom central offices and in data centers. It's not predominant technology yet, but that's the direction they're headed. China has deployed both 380 volts DC and 220 volts DC. And I'm a big fan of the 220 volts DC, and the reason I am is it will work with an existing AC power supply. If you have a 208/240 volt AC input, single phase AC power supply, it'll take a 220 volt DC input all day long and won't care. It'll only use half of the bridge rectifier inside of it and just running through 2 of the 4 diodes. So the reality is that, yeah, you can save a fairly significant amount of money. Anywhere between, the numbers have been run anywhere between 2 and 13% on your energy cost by going to a DC system.
And Curtis, what does that do for your efficiency, or maybe cost of your HVAC system when you go to a DC platform?
Okay, so an interesting point, Kurt. So the DC platform, the HVAC obviously is related to the heat that you release. So if I release 2% less heat from my power conversion, that's 2% less heat that I have to cool. And depends on how efficient my cooling systems are, where I'm located geographically, all that type of thing. But it all plays into the equation, because any heat that you generate and release into the environment, you've got to cool it too. The other part of that is modern data centers use, believe it or not, use DC in their HVAC systems. It's the intermediate stage. They use what's called
Just frequency drives?
Yes, adjustable frequency drives. Variable frequency drives, VFDs. The term wasn't coming to me. So they use VFDs. So in Japan, NTT has done some work where the variable frequency drives that they use over there, the DC input section is 575 volts DC. And so they've taken the rectifier section off their variable frequency drives, and they've done some work where they're running the variable frequency drives straight off of their 380 volt DC plant through a DC-DC converter. So it gets rid of another stage right there. Now the DC-to-DC converter, obviously, any DC-to-DC converter is inefficient too. Just any power conversion is inefficient. There's just no way to get around losses. There's no such thing as the perpetual motion machine yet.
Right.
Don't I think there ever will be.
And with that answer, thank you very much. Excuse me, Curtis. We are coming up on the last 2 minutes, and not really enough time to go into another question for the conference. But as a moderator, I want to thank all my colleagues here on the panel today for participating and just providing great insight and answers to these questions. We had a lot of questions left over, which we pretty much knew we were going to have. But I think this gives us an opportunity to think about doing something just like this again in the future and giving it another go. So I want to thank everybody for joining, and I'm going to turn it over to Jeff for any final comments.
Okay. Thank you, Rick. I just wanted to mention that we're going to give you a 5-question survey with an open dialogue box at the bottom. I just want to be very clear about what the scope of this is, because I know surveys aren't fun, but we really do want to get your feedback on what we did today, how we can improve it. If you wanted to see more, if you want to see presentations, whatever the case may be, really would like to see what you have to say. So in the follow-up of this, we're going to provide a link. It's just basically through Constant Contact, you'll just go in and answer the 5 questions and then give us any comments or feedback that you may have for us. But really do appreciate everybody's time in providing the questions. Like I say, I think we hit about 21 line items out of over 100. So everybody has been extremely involved in making this work. So, and it's supposed to be, again, supposed to be something everybody can participate in from the comfort of wherever you are. So I do appreciate that. And I thank all the panelists for, for giving their time. This took something to put together. So it wasn't just a throw it together thing. We did a lot of organization, making sure this thing was going to be good for you. So I do appreciate everybody's time, and we'll announce the next date if everybody agrees at some point here in the near future. Thank you very much.
Thanks. It's been a lot of fun.
Thank you.
Everybody.
Thanks, everyone. Bye-bye.
Bye-bye.
Thanks, team.